Hi, Phil here again. Welcome to the next video in our modules. And today I'm going to talk about using technology, but in particular talking about the one that we're probably least familiar with, the digital technologies. The syllabus says to us that we must use a range of technology, basic old pen and paper, drawing things, writing things the way we did the last 200 years, all the way through scientific calculator, graphics calculator, using online software and some sort of mainstream packages, things like Excel. So we just got to make sure that we expose the kids to it, and I don't think that we can assume anymore that just because the kids are these born with microchips in them, that they actually know how to use some of these digital technologies per se. I think we have to teach them not just how to use it, but why to use it as well. Why do we use such a range of technology? What's the benefits for it? It actually allows us to start investigating some of these things that we call real world problems. We'll talk about a couple of these later on in the video. Helps the students to sort of start thinking a little bit more about problems. And one of my favourite ones is the what if questions. You know, what if we did change the parameters of this particular problem? How would that affect the outcome? And the kids then don't have to do the great, number crunching that I did when I went to school to get the outcome. 3 weeks later, we've got the new model. We can do that within 30 seconds. And those what if problems allow students to investigate themselves as well. Also within the knowledge and procedures, we talked about that some time ago. One of the key competencies there is to select and use appropriate technology, and we've got to be careful how we do that in terms of asking students to, rather than specifically tell them you must use a graphics calculator, we've got to be careful about whether we can or can't do it, and can we assess the way in which students know how to do things on their graphics calculator is an interesting discussion for another time. Similarly, communication and justification. This is mentioned in there in terms of the using the results of obtained from some sort of technology. We can couch this in terms of using everyday language or mathematical language to make sense of what the outcomes actually are, and I think that to me is that light bulb moment when students then have done it on their graphics calculator, for example. The outcome is, does that mean? And I think that that penny dropping is wonderful for kids. Let's look at an example of how we might use technology, the digital technology, in terms of graphics calculators, Excel or otherwise. One of my favourite ones in terms of introducing students to you can use calculus, we can use exponentials, is I take in 100 dice, and as a class we do this as an activity. When you roll 100 dice, what we want to do is roll 100 dice, count how many sixes there are, take them out, roll what's left, count how many sixes there are, roll what's left, and the discussions and the questions that you ask the students to answer as you go through that, I think give the kids a little bit of an insight into exponential functions, and then how do we get from we talk about a rate of decay, and then we can start talking about the calculus of it as well. And so which is the best mathematical equation which models that particular question in terms of the 100 dice and counting the sixes. So when we actually do that, we get the data and we plot it into some sort of function there, and we get a mathematical equation for it. And the one that I used an online random generator, and I got a non-straight line. I knew that it had to be an exponential, but there's the function and there's the graph that it looks like, and students can then engage in the shape of the function. And then I'd be asking the students, well, now that we know it's an exponential, what does that tell us now? And so making sense of that model in terms of how does that model relate to that particular situation. 109.75, how did that relate to the dice situation? And someone will invariably say it's pretty close to the fact that we started with 100 dice. What about the 0.2? How important is that? And this one here is a little bit more abstract for the kids, and you might lead them into the fact that 1/6 of the dice should be decaying each time, since the probability of rolling a 6 on any one of the dice is 1/6. And so 0.2 is pretty close to 0.16 recurring. One question I've been asked many a time is from teachers as well is why do we use E? Why don't we use a different base? And that's a really good question. I don't think there's any compulsion for us to do that. The reason I use E, because it's a nice easy one in terms of the calculus that we're going to do in terms of deriving these. So where do we go from there? Well, how do we change the model? And you see where this is coming up from what I was talking about before, making modifications to a model. What about if we repeated that same experiment, but this time we took away the 5s and 6s? I wouldn't do this necessarily straight away. What I'd be asking the kids to do would be to predict what would happen. Ask them what if we had to take away the 5s and 6s, and what does that really mean? So we get the kids to predict it, maybe draw it, change their model in a graphical sense. What would it look like if we had to change the algebraic model? Get them to predict those things, and then maybe redo the experiment. It doesn't take very long, and then you can have a look at what the new model is and see whether their predictions meet the outcomes. And I think that's a really good penny dropping moment for kids. Other questions that we might ask along the lines would be, what if we started with 200 dice? How would that change the model? We don't necessarily have to do them all, but we're starting now to engage in the kids in how we might take a particular problem and change it along the terms of those general objectives that I mentioned in a video earlier. And we could talk about decay, but what about if it was something if we started with 50 dice and we did the same thing, but we added to the total each time. Every time we rolled a 6, we added that many dice into the new pot, and we might then have exponential growth. And then how would that change? That negative that we'd have in the original equation then would become a positive. And engaging in these sorts of things, I think, is a worthwhile activity as a precursor to getting into the actual general types of equations and stuff, and techniques that we have to employ. So where does that lead us to? Things like, what about if I had to add matrices? We've talked earlier about the different types of ways in which students learn. If you're a person who likes to tell kids all the time, you can still use your graphics calculator to tell them a rule on how to add matrices, and use their graphics calculators to add sets of matrices together. If you were a person who likes students for them to construct the knowledge for themselves, you might give them the result of adding matrices together. That was close. Adding the matrices together, and ask the students use their graphics calculator to generate a rule on how you might add matrices together. So they change the way in which they're thinking about it. If you can do that, then you can ask them to also, well, let's modify the rule. So we're subtracting matrices, and we're asking then kids to construct their own knowledge. It depends on how you want to, how you think the kids best learn in your classrooms. Further down the track there, we then say, well, again, here's a good way we can use the graphics calculators. Would be, well, what about if the order of the matrices are not equivalent? How do we add a 2x3 matrix to a 3x2 matrix? And when we get this error message up on the calculator, why is it giving us an error? It says you're not able to do it. Why is that the case? And that's again another opportunity for students. Then we're using the graphics calculator not as a manipulative tool, but a thinking tool. And so I think that gives us that opportunity. Lastly, the real world problems are going to go back to the good old exponential problems here. I think at the moment the Gold Coast is riding high on the Commonwealth Games, and we're asking the questions, you know, like how do they know whether they've got enough facilities for it? So real world problems are things like, well, when will the Gold Coast reach a population of 1 million? Is that a really a realistic question? Why do we need to know that? Why do we need to, you know, we need to know this because we need to build more hospitals, more schools, more roads. We need more water. We need more police. We need more teachers. And what's the implications of that? And so I thought myself that was a pretty good question. So what I did, I went to the ABS. You'll notice there that's SBS. That's a totally different channel. You need to go to abs.gov.au. That's well done. I looked at the data from the last 4 census that was conducted in Australia, and you can see there that the data tells me quite easily that the population of the Gold Coast is increasing. So I plotted that onto a graph. I found out what the exponential model is. I did a little bit of calculus in order to do that, and I answered the question. Well, you know what? After all of that background work that I did in terms of developing that rule, that somewhere around the order of about 2050, the population should exceed 1 million people. Currently, it's 500,000 people. So does that mean we're going to need in the next 30 or 20 years, I should say, 20 to 30 years, we're going to need a lot more infrastructure, and what impact does that have on things like the Gold Coast? You might even think of it in terms of population growth in developing countries. And the issue there is that while some of these countries are getting better access to health, and you don't have to look very hard to find the data on some of these countries, say some African countries where they're getting better access to health, their population is increasing beautifully, exponentially, but what impact does that have for access to food as well? So while we can control the amount of health care that people can get, we can't always make it rain. So they're really good, robust discussions for kids to have, and using the mathematics and the technology as the vehicle to get there. So thanks for listening. I hope again this is a little bit of food for thought for you on how you might be able to not just use the technology as a vehicle for actually doing something, but actually getting kids to learn. Bye for now.